Hello students, in today's session we are going to discuss all about aldehydes, ketones, right? So what are aldehydes? Aldehydes, the functional group is RCH4, whereas for ketones it is RCOR, means one of the hydrogen is replaced by alkyl group. What kind of reactions takes place in aldehydes and ketones? Usually in aldehydes and ketones they undergo nucleophilic addition reactions. See, wherever there is presence of double bond, there is possibility of happening addition reactions. In same case, like you seen in alkenes and alkynes, where electrophilic addition reactions takes place, right? But here it's not the electrophilic addition reactions, it's nucleophilic addition reactions. Why is it so? Why it's nucleophilic addition reactions? Okay, nucleophile means the species which enrich in electrons, whereas in the carbonyl group the carbon is always positive and oxygen is negative, right? So the nucleophile can attack this carbon, making this happen. Okay, now I have another aldehyde, the basic aldehyde, which is formaldehyde. There is another aldehyde, acetaldehyde and acetone. Among these three, where do you think that nucleophilic addition reactions takes place faster? Of course, nucleophilic addition reaction takes place in each and every case over here. But where exactly they take faster? They happen faster. In case of formaldehyde, what is the reason? The reason behind it is, first is plus I effect. A second thing is steric hindrance. Both is negative, in the sense there is no plus I effect, there is no steric hindrance. That's the reason why formaldehyde, the nucleophilic addition reactions in formaldehyde happens faster. Whereas in the case of acetaldehyde, what happens? Due to presence of methyl group is an electron donating group. So it stabilizes the carbon, and carbon doesn't want a nucleophile to attack, because it is getting stabilized by adjacent methyl group, which is an electron donating group. In case of acetone, you have two methyl groups and it is highly stabilized, as well as there is steric hindrance for a nucleophile to attack this carbon. That means due to plus I effect and due to steric hindrance, the nucleophilic addition reactions in acetone is far lesser, because the carbon is already stabilized due to plus I effect. Moreover, they allow, that means the methyl group present over here does not allow the nucleophile to attack this carbon, right? Apart from nucleophilic addition reactions, what sort of reactions you can expect in aldehydes and ketones? So I can think of addition elimination reactions. What is it? Initially addition takes place, followed by elimination. Okay, and the most famous reactions for aldehydes and ketones are named reactions. There are a number of named reactions which you need to memorize in this unit, especially aldehydes and ketones. Moreover, aldehydes and ketones forms the basis for oxidation and reduction reactions too. Means aldehydes can reduce to alcohols and they can be oxidized to carboxylic acids. If you have an aldehyde, say it's formaldehyde or acetaldehyde, it can be reduced to alcohols, whereas they can be oxidized to carboxylic acids, right? So these are certain types of reactions. Okay, so what basically you need to learn in this chapter is the characteristic reactions of aldehydes and ketones, the named reactions, oxidation and reduction reactions, as well as the chemical tests. Okay, you need to understand the chemical tests: Swift reagent, 2,4-DNP, ammonical silver nitrate solution, that is Tolin's reagent, okay, Felling's test, Benedict's test. So there are a lot of tests, chemical tests, which you have to learn in this. Okay, so keeping this aside, we'll discuss some of the questions from the previous questions, right, which were asked in the JEE Mains. Okay, so look at the question over here. In the following sequence of reactions, They are asking what is the compound D. Okay, leaving the options aside, let's see what exactly the equation is all about, the reaction is all about. They have been given with a primary alcohol, that is ethanol. Ethanol, when treated with red phosphorus, usually with iodine, there is replacement of this OH, means the compound A is CH3CH2I. This, when treated with magnesium, you have seen this, right? In the alkanes, magnesium undergo insertion reactions because the magnesium is a divalent metal. So it undergoes insertion, means it gets inserted between alkyl group and halogen, like this, in this way. CH3, CH2, Mg, I. Okay. Now, if where is a positive and where is a negative charge here? You have negative here, positive over here. When this reacts with your aldehyde, the actual aldehyde is formaldehyde. You know, formaldehyde is polar, where you have positive and negative. Let's see. If opposite charges attack, what happens? So, the negative attacks to this negative attacks to this, which leads to the formation of, I'm just adding it, look at this, CH3, CH2, this gets attached to this carbon is having 2 hydrogens, and O, Mg, I. This is what is, there is formation of adduct. This on hydrolysis, what happens? Whenever you are doing H plus means acid, H plus slash H2O means acid hydrolysis, just H2O hydrolysis. What is the difference between hydrolysis and hydration? Hydration is addition of water, hydrolysis is lysis, that means breaking of molecule due to addition of water. So here also, whenever I'm adding water, molecule is breaking due to addition of water, like this. This is hydrolysis. Hydration is simple addition, where in case of alkenes you have seen hydration reactions, where hydrogen is attached to one carbon, hydroxy group is attached to another carbon. Now what is the product here? CH3, CH2, C, OH, this is H and this is H, plus Mg, divalent, right? So iodine, hydroxy. What is the name of this compound? Let's figure out. Okay, I have, say this is 1, this is 2, this is 3. This is propanol, right? This is propanol. Now, where is propanol? Yes. Got it? This one, N-propyl alcohol. This is propanol, means this is aldehyde. CH3, CH2, CHO. This is propanol, Al. N-propyl alcohol, this is straight chain alcohol, like this. The same thing can be written in this way, CH3, CH2, CH2, OH, N-propyl alcohol. So it's not N-butanol, this one. See, these two can be eliminated at the start of the reaction because you need to count the total number of carbons. There is 1 carbon, 2 carbon, and nowhere in the reagents or anywhere there is extra carbon added, and this is the 3rd carbon. So the whole reaction itself, you will be end up with the 3 carbons. So these 2 options can be eliminated at the start. Okay, so N-propyl alcohol is the answer. It's not the propanol. So even in the exam also, don't look at the options before solving the question. Look at the question, understand it, write down the answer, then look at the options, whether whatever you are end up the answer, whether that option is there in the given choice. That helps you to score even better. Instead of looking, because options are the one that will deceive you. Okay, once you look at the options, immediately you will fall into confusion. Oh, I thought like the reaction happens like this, but it's not happening like this because there are other aldehydes are also involved. So is it aldehyde involved in this? So these are the certain doubts what you get. So forget about the options, solve the question, right? Now you are end up with the answer. Now check the answer whether it is there in your options or not. If it is there, that's perfect. If it's not there, just go back and check it, so that it is easy to understand where exactly you have committed the mistake. And in this way, you will really score a better. So hope you understood this. Moving on to the next question. Phenyl magnesium bromide reacts with methanol, okay, to give, okay, let's, as I said you before looking at the structures, let's write down this. Phenyl magnesium bromide. What is phenyl? Phenyl magnesium bromide, MgBr. Okay, before that, let us write down the very positive, because once you are writing a Grignard reagent, definitely there is presence of negative and positive charges, right? So now where is present? Where is negative? This is negative. This is positive. Okay, reacts with methanol. Let's write on the structure of methanol also. CH3OH. Can we make positive and negatives here also? Okay. Negative, this is positive. As we have done, opposite charges attract. How? Look at this. This O minus attacks magnesium. This negative charge attacks hydrogen. Now there is formation of benzene, and you have hydrogen here, plus MgBrOCH3. I'm end up with this. Shall we check whether the options of these are available or not? Okay. So benzene, right, I have here, and there is nowhere benzene, so I can eliminate because benzene is present only here. Okay, so MgOMbBr, OMb, both are similar, right? Bromine. I hope you got it, right? This is the way how do you proceed with the questions. So once you are writing with the Grignard reagent, just write on where is a positive and where is negative. Remember students, Grignard reagents, when treated with acids or water or polar solvents like methanol or ethanol, they always forms alkanes. This is a side reaction that happens usually. Okay, this is a side reaction. Usually this is not the purpose what we are using, that means for what the Grignard reagent is prepared. Grignard reagent is usually prepared to treat the aldehydes or ketones, where you can get the primary, secondary alcohols, tertiary alcohols like this. But this is the side reaction. Side reaction in the sense like, if assume that you have a Grignard reagent, okay, and if the bottle of the Grignard reagent is kept opened, what happens? It reacts with the moisture present in the air and it converts to alkane. Say for example, I'll take an example of CH3MgBr, methyl magnesium bromide, when treated with water. That means what happens if it is exposed to moisture, right? Just see what is there. CH3, this is negative and hydrogen is positive. It reacts with hydrogen plus MgBrOH. Methane, this is not the purpose. That means if you want to prepare methane, it's not like I have to take the Grignard reagent, proceed. No, this is a side reaction which we don't expect, which we don't want to. But still, if you are not taking proper precautions during your laboratories, then that's what is going to happen. That's what, whenever we are doing an experiment also, the Grignard reagent is kept far away from the acids, because even the fumes of the acids can convert the Grignard reagent to alkanes. Okay, in the same way, here also, phenyl magnesium bromide is treated with protic solvent, right? So what happens? It is converted to benzene. So this is one of the questions which was asked in the main 2006. Hope it's clear to you. Moving on to the next question. Okay. Among the following, the one that gives positive iodoform test upon reaction with iodine and sodium hydroxide. Sounds interesting. Okay. Iodoform test. Okay. Iodoform test will be given by this one. CO CH3. That means compounds which contain COCH3 are compounds which contain CHOH CH3. This one and this one. If you have any compound which consists of COCH3 at any given change, at any given chain, then this compound can give you positive iodoform test. Or if a compound has CHOH3, then again it gives positive towards the iodoform test. Okay, so iodoform, what is iodoform? You know chloroform, CHCl3, iodoform, CHI3. Okay, CHCl3, chloroform, CHBr3, bromoform, is the same as CHI3, iodoform. So any compound which consists of either this requirement or this requirement, when treated with iodine in the presence of sodium hydroxide, they respond positive towards the iodoform. Can you find out where exactly this group is present here? What is the option now? We have 4 given options. Which is that? Where you have this. The first one, CHOH. Right? CHOH is present, but not CH3. It is CH2. No. This will not give you. A second one, you have CH2OH. No. Yes, here you have CHOH, but again CH3. It's not directly CH3. No. Here you see. I'll write on this structure again for you. pH means phenyl. Then you have CH. You have OH. Then CH3. Right? This group. So this compound gives positive iodoform test. Is it clear, students? This is how you identify the aldehydes or ketones. So this is ketone, this is a secondary alcohol. Okay, moving on to the next question. 2-methylbutane on reacting with bromine in the presence of sunlight gives mainly. Okay, as I told you earlier, please don't read the options. Let's understand the question first. Let's look at the structures. Let's write on the structures. Understand what kind of reaction can take place. Okay. See, I'm covering all the questions because we have completed hydrocarbons. We have completed haloalkanes and haloarenes. We have finished with the alcohols, and now today we are in the aldehydes and ketones. So this is a cumulative exercise. Like whatever, not only the aldehydes and ketones, we are also accumulating the whatever we have completed the portion, so that we get enough practice to solve. Okay, so this is one of the question from alkanes and alkenes. Okay, so because you can take this one into your practice. 2-methylbutane. Okay, so don't write the structure directly. But means 4 carbons, 2-methyl. 2-methylbutane. Yes, I have written it. Now I'm just making up the valencies of the carbons, right? When treated with bromine in the presence of sunlight. So whenever you see in the presence of sunlight, yes, what do you remember? The mechanism happens by free radical substitution mechanism, right? Free radical substitution mechanism means the bromine is broken down to form the free radical. This free radical, what happens in the free radical substitution? It abstracts the hydrogens. So which hydrogen? There are a lot of hydrogens here. Which hydrogen can be abstracted? Okay, let's see. Like abstracting different types of hydrogens. Now, this is a primary carbon. Hydrogens attached to the primary carbon are primary hydrogens. This is a primary hydrogens. These are the primary hydrogens. This is a secondary carbon and hydrogens attached to the secondary carbon are secondary hydrogens. Whereas this is a tertiary carbon and this hydrogen is a tertiary hydrogen. So if you remove these hydrogens, the product will be same because everything is a primary. So I'll replace anyone saying like this: CH2 Br CH CH3, rest of the molecule remains same. This can be one product because this hydrogen is abstracted by bromine. Okay, I'll replace the secondary hydrogen now. Say CH3 CH, CH3, then CH, Br. This hydrogen I'm replacing now. Yeah, this is one kind of compound that can be expected. Well, another one, when you replace the tertiary hydrogen, you get C, CH3, CH3, bromine gets attacked here. Okay, this can be the products that can be expected from this reaction. So before the attack of bromine, what is the intermediate formed? Free radical. Where the free radical lies? Here, or here, or here. Which free radical is more stable? Tertiary, or primary, or secondary? Which free radical is more stable? Tertiary free radical is more stable, right? Because of the presence of electron donating group surrounding it. There are 3 electron donating groups, and because of the plus psi effect and hyperconjugation, tertiary free radical is more stable. So more the stable the free radical, more it is to form the compound. So I expect this compound to be formed because of the stability of the free radical, not the first or 2, right? So what is the name of this compound now? Because you have been given with this, not the structure, with the IUPAC names. Write on the structure name of this compound. It's 1, 2, 3, 4. 2-bromo, 2-methyl butane. Where is it? It is here. 2-bromo, 2-methyl butane. If you look at the options, see here. 1-bromo, 2-methyl butane. Yes, this is present here. See. Look at this. You have 2-bromo, 3-methyl. 2-bromo, 3-methyl butane. Yes, this is also present here. Yes. That means where exactly you can commit the mistake, those options are also present here. But what is the concept overall? You need to find out the stability of the free radical. Yes, free radicals are stable. Which free radical? Tertiary free radical. How? By either plus psi effect, that is inductive effect, or hyperconjugation. We have discussed in detail about these 2 concepts earlier. 1-bromo, 3-methyl butane. Yes, this can be possible, right? So hope guys it's clear to you. Okay, moving on to the next question. Bottles containing C6H5I. This is phenyl iodide, right? And C6CH5 CH2I. This is benzyl iodide. Okay. There are 2 compounds given. One is phenyl iodide, another is benzyl iodide. Lost their original labels. Okay. So we don't know now what we know. There are 2 compounds. One is phenyl iodide and one is benzyl iodide. So, but we don't know which bottle contains these. Now they were labeled A and B. For testing A and B, so we were taken separately in test tubes and boiled with sodium hydroxide. Yes. The end solution in each tube was made acidic with dilute nitric acid, and then some silver nitrate solution was added. Substance B gave a yellow precipitate. Yeah. Which one of the following statements is true for this experiment? So they have given A was this, A, B was this, and addition of nitric acid was unnecessary, A was 6. Okay, so this is usually silver nitrate test. Silver nitrate test. Silver nitrate test, okay, is a test for distinguishing haloalkanes from haloarenes. Means haloarenes do not respond to this test, whereas haloalkanes they give positive to this test. Why haloarenes do not respond to this test? Because haloarene means this one, they have a resonance, and moreover this lone pair of electrons on the iodine, when they participate into the delocalization or resonance, they develop a double bond character, which is more stable. That means if replacing iodine from here is very difficult, whereas replacing iodine from here is easy. See, this is not a haloarene. C6H5, if it is directly attached to the benzene, that gives you haloarene. This is not a haloarene. CH2I, this is a haloalkane only. This iodine can be easily replaced. So silver nitrate test is a test used for distinguishing haloalkanes from haloarenes, and haloalkanes gives positive to this test. Okay, haloalkanes positive to this test in the sense substance B gave a yellow precipitate. So what is substance B? Substance B is this. Means where is this? A was C6H5? No. B was C6H? No. Substance here. Addition of nitric acid was unnecessary, and A was C6H5I. Yeah. If substance B is this, then substance A should be this. They have not given you the option that substance B is this. No, there is no such option. But you know that substance B is this. So obviously substance A should be this. Right? So that is how you have given the question. Now, with the help of silver nitrate test, you can able to identify the color of the compound also, like color of the halogen. For example, if you have a fluorine, fluorine does not give any precipitate. Okay, they just form a solution. But if you have a chlorine, they form white precipitate. If you have a bromine, it gives you cream precipitate. If you have iodine, they give yellow precipitate. Okay, that means based upon the color of the precipitate also you can able to identify the halogen that is present. Usually we can find that is a haloalkane, but in haloalkane what is that halo also we can find out. If you get a clear solution, then it is fluorine. Haloarenes does not respond. That means whenever you are adding reagents, the just reagents will be as such. There is no reaction takes place. Whereas in the case of fluorine, reaction takes place, but the clear solution is formed. In case of chlorine, white precipitate, bromine, cream precipitate, iodine, yellow precipitate. You can just remember this as milk, cream, butter. The color of milk is white, cream is cream color, butter is yellow color. In this way you can remember. Okay, so this is all about the silver nitrate test. This was the question asked previously. So that means we have seen as of now 2 questions asked for chemical test. One is the iodoform test, other is the silver nitrate test. So even the chemical tests are very, very important for the exam point of view. Let's look at the next question. Alkyl halides react with dialkyl copper reagent to give. Okay, alkyl halides, let's write down like this. Treated with dialkyl copper, Gilman reagent we call as dialkyl cuprate. Okay, this is called Gilman. Where we have seen this? Remember, students, dialkyl cuprate lithium. Preparation of alkanes. Please go back and check it. Okay, the preparation of alkanes. So this is one alkyl. These are the again alkyl groups. Means I can prepare alkanes. That means if you take a lower alkane, I can prepare higher alkanes from it. So I have, say for example, I have methyl chloride. From methyl chloride, I can prepare ethane. That means from lower alkanes, I can prepare higher alkanes. From where you are getting extra methyl group? From the reagent. The reagent itself is a dialkyl copper. Got it? If you remember Wood's reaction, remember it. What does Wood reaction? Wood's reaction is RX, alkyl halides. When treated with sodium, that means 2 molecules of alkyl halides, there is elimination of minus NaX, that means 2 NaXA. This is 2. Formation of RR. Means from alkyl halides, I am preparing alkanes. But what is the use? But lower alkyl halides, I am preparing higher alkanes. Okay. So in the same way, even Gilman reagent is also useful for the preparation of alkanes from lower to higher. Yes, this is something interesting. Okay, so which compound would give 5-keto-2-methyl-hexanol upon ozonolysis? We have seen about ozonolysis, right? Let's draw the structure of this. Yes. 5-keto-2-methyl-hexanol. So instead of this, let's make hex in the sense 1, 2, 3, 4, 5, 6. They have written hexanol. All means aldehyde. Aldehyde. Yes. 2-methyl. Okay, as this is the first carbon, this should be 2, not from this side. Okay, this should be because aldehydes, the functional group start carbon number 1 will be here, followed by 2 methyl, 5 keto. So 1 2 3 4 5 keto of oxo. Yeah, rest make it the valency of the carbon by adding up the hydrogens. Yes, in this way. Now, when do you get this compound upon ozonolysis? I already told you how do you find out the products of ozonolysis, right? If you remember. Say for example, if you have a compound, say CH3, CH, double bond CH2. What if this compound undergoes ozonolysis? I told you. What you do? Break this bond, add one oxygen here, add one oxygen here. So there are 2 products. What are the 2 products? CH3, CHO, this one, plus CH2O, means formaldehyde, HCHO. Understanding? Ozonolysis is very simple. Wherever you have a double bond, just break the double bond, add oxygen on either sides. You get 2 compounds. But as this is a cyclic ring, if you break a double bond and add oxygens on either side, you get one single compound, but the chain is opened. The cyclic ring is opened. Okay, shall we try breaking option 1? Look at the option 1. I'm breaking it here, adding oxygen. Okay, so CH3, I'm just writing for your ease the same way. Okay, right, then CH3, yes, you have CH also here, then you have double bond O, and this side also one double bond O, double bond O. Understanding? I just have broken and I have written the structure. If you convert this into normal structure like in this way, CH3, okay, at one side it has C double bond O, then you have attached to CH2, then CH2, then CH, CH3, then C double bond O, and you have H. Look at this. Are they both similar or different? That means with the help of first structure only we could have been able to identify. Okay, even if you could try with these also, you won't get the similar of this. They both are same. Look at this. Are you understanding? Usually you get 2 products, but here also you get 2 products, but as this is cyclic ring, when you are breaking, the ring is opened up, but you are getting only one single. So ozonolysis is very quite easy. Break the double bond, add the oxygens on either side of the double bond, that's it, you get the product. So I'll move to the next question. So this was the question which was asked in mains 2015. So I'm picking up one more question here for you guys. Sodium phenoxide, when heated with carbon dioxide under pressure at 125 degrees centigrade, yields a product which on acetylation produces C. Now you need to find out what is C. So the best thing is that, you know, whatever they have asked here, the same structures were given here, right? Sodium phenoxide. So let's make it very simple. O minus Na plus is sodium phenoxide. When treated with carbon dioxide, gives B. Do you remember? I'm asking you guys, do you remember this named reaction? Sodium phenoxide with chloroform and sodium hydroxide is a Reamer-Tiemann reaction, right? Reamer-Tiemann reaction. Sodium phenoxide with chloroform and sodium hydroxide. That's Reamer-Tiemann. This one, carbon dioxide. This is a coal-base reaction. Coal-base reaction. So in coal-base reaction, you are preparing salicylic acid. Reamer-Tiemann reaction, you are preparing salicylaldehyde. I'm just writing out the structures for you. Okay. If you have phenol, COH, this is salicylic acid, because when you are writing carbon dioxide, this carbon dioxide is here. Okay, and the hydrogen of the carbon only, this is the hydrogen of the carbon. Okay, so carbon dioxide gets inserted, that's it, between the carbon and hydrogen. between the carbon and hydrogen, carbon dioxide gets inserted. So you get acid. So already phenol is present. So this is salicylic acid. Whereas with chloroform and sodium hydroxide, you get salicylaldehyde. This is salicylaldehyde. That is Riemann-Tiemann. This is Kolbe-Schmidt. Got it? So I understood that my product here, the B is, I'll write on the structure of B here. Guys, please look. I'm not writing the structure of the final structure. I'm writing the structure of B, O minus, Na plus and COOH. When I'm doing acid hydrolysis, okay, I'm doing acid hydrolysis, this converts to like this. COOH will be intact as such. O minus Na plus is converted to H. This acid is converting here. Sodium is eliminated. Is a metal. I'm dissolving the metal. That's it in the acid. So the proton on the acid attacks here. Now I'm getting the salicylic acid. But there is one more reagent present. AC2O. AC is acetyl group. 2O means like this. CH3 CO O CO CH3 acetic anhydride. This is acetic anhydride. Now acetic anhydride when treated with phenols, very nice reaction. See, I'm writing the structure OH, sorry, COOH here, O CO CH3 means here this hydrogen is coming here and is eliminated as acetic acid, whereas acetyl group, that is COCH3 group, is attacked here. Where is this present? Yes, I can see. That means, see, though we are getting different structures, but you can see carboxylic acid and acetyl group, that is acetoxy group, present ortho to each other. I'll go here because COOH and OCOCH3 are present ortho to each other. This is O minus Na plus can be anywhere, right? So even to confuse you, they have just rearranged these. Are you understanding, students? Any queries so far? Right? You understood this question? Okay. So this is B is Kolbe-Schmidt. The most suitable reagent for the conversion of alcohols to aldehydes. This is primary alcohol. You get aldehyde. You know, right? How would you convert alcohols to aldehydes and ketones? Or yeah, primary alcohols gives you upon oxidation. Primary alcohols upon oxidation gives you aldehydes. Secondary alcohols upon oxidation gives you ketones. Whereas tertiary alcohols upon oxidation, no. That means tertiary alcohols are inert to oxidation. Exception is concentrated nitric acid is the one you can use it. Concentrated nitric acid, with the help of concentrated nitric acid, tertiary alcohols can undergo oxidation. Please go back to Popov's rules also. Popov's rule. Okay, once after the completion of class, just check back what is this Popov's rules is all about. Okay, coming to the question. Primary alcohols is converted to aldehydes, right? Now, usually primary alcohols convert to aldehydes, and these aldehydes can be converted to acids. If you want to stop here, then you should not use powerful oxidizing reagent. Use a mild oxidizing reagent, then this step can be prevented. Potassium permanganate is a very, very good powerful oxidizing reagent where alcohols can be converted directly to carboxylic acids. Potassium dichromate equally, they both are equivalents. Even potassium dichromate can directly convert alcohols to carboxylic acids. Even chromium trioxide. Okay, usually chromic acid. Okay, but PCC, what is PCC? Any idea? Pyridinium chlorochromate. What is pyridine? N, like this. Now this is onium, means you have a positive charge. Pyridinium, onium. Chlorochromate. So you have a chlorine, chromium, O negative here. That means we have positive here, negative here. Pyridinium chlorochromate, PCC. This is the reagent which can convert the primary alcohols to aldehydes level only. The further oxidation is prevented because this is a mild oxidizing reagent. Got it, students? This was a question which was asked in Main 2014. Okay. A question in Main 2013. An unknown alcohol is treated with Lucas reagent to determine whether the alcohol is primary, secondary or tertiary. Yeah, we know that. Lucas reagent is the chemical test used to distinguish primary, secondary and tertiary. Which alcohol reacts fastest and by what mechanism? Do you remember Lucas reagent? What is Lucas reagent? Zinc chloride plus HCl. Zinc chloride plus HCl. Can you tell me which alcohol gives positive test? Yes, we know Lucas test is the test to distinguish primary, secondary and tertiary alcohols. And we know Lucas reagent, zinc chloride and HCl. So, which alcohol can be identified? Okay, tertiary alcohols gives positive test. That means when treated tertiary alcohols with zinc chloride and HCl, immediately they form white precipitate, white turbidity we say. Whereas secondary alcohols forms white turbidity after 10 minutes. Whereas primary alcohols, they do not react at all with this reagent. Means what did you understood? Tertiary alcohols gives positive test. What is tertiary alcohol? CH3 OH. Tertiary alcohols gives positive. Now, how do tertiary alcohols react? By which mechanism? Tertiary alcohols should form tertiary carbocation. Tertiary carbocation means, yes, I have the option here, tertiary alcohol by SN1 mechanism. If you think that primary alcohols gives positive test, then you have there is no such option. Okay, this option can be ignored easily because tertiary alcohol is not primary alcohol by SN2 mechanism. Now secondary alcohol by SN1, secondary alcohol by SN2. Yes, is the tertiary alcohols that gives immediately the white turbidity, and tertiary means they take part usually by SN1 mechanism due to formation of a stable carbocation, that is carbocation, tertiary carbocation. Again the reason being the same, plus I effect, hyperconjugation. Due to formation of more hyperconjugation structures, they stabilize the carbocation. So this carbocation will be happy to lose the hydroxide group. Yes, because even after the loss, it can bear the positive charge because this positive charge is supported by methyl group surrounding it. So with this we have come to an end to the session, students. Any doubts so far what has been taught to you? Please put on the chat or write the comments. We'll get back to you on this. Thank you guys. We'll come with the next session with another chapter. Thank you.